Hello friends, this is Daminado Cap and today I'm going to talk about cosmological model with data analysis. So previously I have made a video and shown you that how to install some software and you can use those software to work with the data and you can fit your model, whatever model you have. So today we are going to understand the code and also we will see that how these models can fit with data. So let's get started. So before jumping into the code, we have to first understand that basically what is the algorithm we have to first develop in order to, get some idea that, okay, basically what is going on. So first of all, I'm going to get into that point that what is the meaning of having data and fitting the model. So first of all, very in a layman term, for an example, you have, let us say, you have something, for an example, let us say you have distance, right? And there is a time. Suppose that somebody has done an analysis and they have got few datas with time. Let us say time is starting from 0, 1, 2, 3, 4, and they have measured the distance and so on. And from this distance, they try to understand that what could be the relationship between distance and time. Before that, they did not have any idea that what is the relationship between distance and time. They just measured that, okay, they have used and they just measuring the distances. But they don't have any idea that how this distance is correlated with time. So now they have, there are few scattered of data. So you can see that if you can, simply execute that something like over here, then you can understand it. Okay, if we can plot a straight line, then this straight line will show that distance is equal to time. So let us say this is y is equal to t. So I can say that y is equal to m times t plus, let us say, c, where m is the slope, right? And c is some kind of constant. Let us say at 0, this is not, this is hitting over here, right? So now from this data set, you can extract that the slope has to be, if it is a constant, slope has to be constant. Let us say slope has to be constant, and c0 is also a constant. So in some sense, you can easily find out from this data that what is your constant, and this constant will not change with time. That is the meaning of constant, right? So that is the thing. So before you know, now you are having some model and you try to estimate these m0 and c0 by fitting some model. So this is y is equal to mt plus c is your model, right? Similarly, some can say that, okay, no, we can also fit with some polynomial. Let us say a of t, and let us say a plus a of t plus a1, a2, and a3 of t square, right? So this is again a parabolic type of fitting, but you can have it in the lower t. It is going with a straight line. It is varying with a straight line because for t is lesser than 1. So this part will be dominating, and over here as t is going bigger than 1, then this part will dominating, right? So for some part, let's say from here to here, it is dominating with a straight line, and then it will grow with the parabola. So it may have, you can also get from a1, a2, and a3. But the problem is that when you have these actual points, right? So these black points are the actual points, and now you are trying to estimate what could be the by fitting it. Like let us say t is equal to 1, and you have estimated it, okay, m should be there and c should be there. So you have to first assume that, let us say my m should be let's say 3 and c should be, let us say, 2. Now what you can do is that you can scatter this m3. Let us say your m3 should vary from -1. So 0 cannot be possible. So what you can do is, let us say you are having 0.01 to, let us say, 4. So m can vary from 0.01 to 4. The problem is that how you know that this is the value. So you have to first understand your model, because you are building your model. So you know that where is your parameter, what is the parametric space of the m, right? And then again your c can be 2, so it can go from, let us say, -2 to 2. Okay, so here you have the medium value that, okay, it is my guessing value. So you are trying to guess this is called the prior, that what should be the prior of this model, right? So this is we call prior. M could be 3. Now I'm going to scatter from minimum value to maximum value. On the other hand, similarly, c is equal to 2 -2 to 2. It can go. Now it will try to use the MCMC algorithm. So it is try to, scatter, it's try to make some kind of, sampling process. Okay. So it will try to sample those priors, m is equal to 3, 0.01. So it will make various combinations from 0.010 to 4 and minus 2 to 2, and try to minimize between the data, that okay, how we can minimize it. So there is an, again, algorithm says that okay, minimize it. So this is called the optimization process happen. And then it tries to fit that okay, this is your true value. So let us say this is your true distance. Okay, this is the calculated distance, and since somebody has already estimated that what could be the error, and this is the error. Okay, whatever the error is in the data, and now it will give you the chi-square. Chi-square says that you have a calculated the distance at different point using your model, using the priors. The priors will try to calculate, estimate everything at same time. Let us say, for example, M3, it had selected 0.01, it is selected 0.1. So for each and every data, it is trying to, calculate everything. So there is a list going on. Over here, you have a list going on. So true distance has its own list. Calculated distance has its own list. And you have also the error of the list of an error, and from there it tries to calculate the chi-square. And once you have calculated the chi-square, it tries to say that okay, is it very much close to 1 or not. And there is again a call reduced chi-square, it has to be lesser than 1, right? So if you are building some model and you are trying to fit your chi-square is approximately 1 and your reduced chi-square has to be lesser than 1, then you can say that okay, your model is very aggressive. Now, whatever I have given you, the toy model, it is appearing that, okay, it is a very simple. You have to just you have to first guess it according to your model that you are trying to develop, and you have to find out the chi-square. And once your chi-square is done, okay, if chi-square is coming out to be lesser than 1 or approximately 1 and 2, and the radius chi-square has to be lesser than 1, then you can say that, okay, we have a nice fit of model. Okay, very good. So for the simplified models, it's very amazing that y is equal to mx plus c and so on, right? But what happens if you try to work with the cosmological data? Now, cosmological data in which we are trying to estimate the H0, which is the Hubble constant. Okay, so there is an Hubble which is depending on the redshift, which is usually defined as S0, and we can say that okay, there is a constant arising, which constant is basically h of z is equal to 0. We can estimate h of z is equal to 0 is S0, right? Now H0 for the universe, for the expanding universe, has to be constant because it is a constant, right? Just like a gravitational constant, speed of light is a constant, Planck quantity is a constant, right? So these are the constant which will not vary, right? So in order to understand how we can extract the expansion rate of the universe, we have to first define a model, because without the model, you cannot estimate what is your H. So now the problem is that there are various things from which we are getting the light. So we had the Hubble telescope, okay, Hubble Space Telescope, and now we have JWST, James Webb Telescope, right? So again, we have the CMB, cosmic microwave background radiation, right? And similarly, we have different sources. We have galaxies. We can measure the weak lensing, gravitational lensing. We can measure the some light coming from the galaxies, and we can estimate everything. So we can have different sources. We can have different data, and then as we are looking at a very greater length of sources, means that as you are going at the past, means that your z is becoming higher. So your z is starting from 0, which is at present 0. Let us say 1. Again, you are going back to the past. 1 is higher past, 2, 3, 4, and similarly it will go on, right? So as you are getting the light away and away and away, you are actually going to looking at into the past of the universe, right? So that is how Z is running. So whenever you will see the data against the redshift, it is not talking about anything which is in future, right? You can interpolate it. So let us suppose that I have a straight line from here, then I can interpolate to this one, right? So everything we are actually estimating against H. Let us say we are trying to estimate Hz. So here you have z is equal to 0, z is equal to 1, 2, let us say 3, 4, 5, and so on. Okay, so now you can try to estimate what should be the z. So we have the data like this and like this and like this and like this and this, and then we can try to figure out which model is suitable for this at z and so on. And from here you can see that okay, z0 this one, so we can interpret this one as a h0, right? So this is the expansion rate of the universe, which has to be constant at every time, right? So this is the idea of determining h0 from the data. Let us say we have the Cepheid variables, we have supernova data, and from the supernova we try to we are using the brightness calculation, and from the brightness we can estimate the h0. So now the problem is that when you are entering the cosmology, we have the various formulas, not formulas, we have the various ways to estimate something. We have something, let us say x, y, z, and we can correlate with different things, and we can say that okay, this is how something is correlated, and from there we can estimate h0, and we can predict so many things about the universe. So the most popular and simplified model is Lambda CDM model, which I have already discussed various times in this channel, right? So in the Lambda CDM model, we are treating dark matter as a cold dark matter whose pressure is equal to 0. Let us say equation of a state which is equal to P over rho can be 0, right? And omega is equal to -1 because it is a lambda constant. So the equation of a state becomes -1. So the standard equation is 3h square is equal to, let us say, 1 over mpl, which is the mass of Planck square, is equal to rho m. Let us say this is the dark matter, and this is your, let us say, rho density, which is coming from the dark energy. And sometimes people also taking care of the curvature, let us say k and so on. So now for an example, we are not considering that one. We are just considering that there are two things, because when we are at the late time phase, means that when you are at, let us say, z is equal to 0 to 5, this era is called to be the late time phase, means that the present time phase of the universe, and the universe is basically coming to the accelerating phase just now, just recently, like z is equal to 0 to, let us say, 0 point, let us say 2. Okay, so this is the era at which universe has now picked the acceleration and is trying to show the acceleration. So before that, there was no acceleration, there was an expansion of the universe. So there are different phases. We have already discussed that there is a matter phase and there is a dark energy phase. And now dark energy has dominating, starting to dominate just now. Okay. And now the second equation, you have 2s dot is equal to 3h square, which is called the second Friedman equation, which is again -1 over mpl square into pressure of matter and pressure of this one, right? So now when you are using the Lambda CDM model, you have two components. So you're trying to understand the continuity equation, which can be given by del mu t mu nu, and whatever the component, it has to be 0, because if it is a minimally coupled, so I can have that rho m dot plus 3h rho m plus pm is equal to 0, and similarly rho lambda dot 3h rho lambda plus p lambda is equal to 0. So these are again the equation of motion, you can say, for the fluid. So these are the continuity equation, and we have this Friedman equation. Now, what is the way of explaining it? So we are trying to estimate S0. So what we can do over here, we can say that, okay, we have omega m0, which is again a constant. I can label it as a 1 by mpl square. I can write kappa square. Okay. So kappa square rho m 0 over 3h0 square. Now this quantities I am calling as a rho omega m0. This is called the fraction density, which is again a constant, right? It is not changing because everything is constant. Kappa is constant because mass of Planck length constant, 3 is constant, rho m0 is constant, h0 is constant. It is not changing. It is not a function of redshift. On the other hand, you have rho lambda. So I can just estimate rho lambda 0 is equal to kappa square rho lambda 0 over 3h not square 0. Now you may say that, okay, why you are doing it? We are actually trying to get from h0. So what we can do, we can use this equation 3h square. So I can write over here h square is equal to, if I am just dividing with h0 square, then I have kappa square h0 square with 3h square, and then rho m plus rho lambda, right? Now from these equations, equation number 2 and equation number 3, I can easily solve these equations, right? So if you try to solve this equation, let us say rho m dot. So I can just say rho m dot is equal to 3. Let us say minus 3. Pm is equal to already 0. H is equal to what? dA over E dt. Correct? And rho m I can write rho m by dt. Isn't that? So this is your rho m. Now this dt can be cancelled out. So I got here d rho m over rho m is equal to minus of dA over A. I can say this is, now again we are trying to integrate it. Now integration can be done from now, because now we are observing. So now means that when you are trying to use the scale factor, there is a relation called A is equal to 1 over 1 plus Z. What I already said, that when Z is equal to 0, it is your now present. And when you have Z is equal to infinite, it means that now you are looking at the very big bang. So what happens is that when your Z is very increasing, A is going to be decreased, means the A is going to be 0. And now as you are increasing, as you are coming towards Z is equal to 0, then it is your A becomes 1, right? And if Z is equal to minus 1, it is the future epoch of the universe, correct? So as we are looking back into the time, Z will increase, so A will decrease. So so first of all, I am saying that now I am here, so A is my 1. And at this moment, you have the energy density of the matter has to be 0, rho m0. And as we are looking into the past, let us say any time we are looking into the past, because I am not saying that infinity, because we have some set of variables. When any telescope is looking into the past, it is not completely seeing into the infinity of the universe or the complete beginning of the universe. It has some restriction. It can, get the data from different redshift. So A is labeling that, okay, which redshift you are talking about, right? And at this point, I can say that, okay, rho m is again some kind of, a variable. So over here, I can have a log of rho m over rho m0 is equal to minus of 3 log of A over 1, correct? Okay, sorry, I'm not taking too much step. So I can just say, okay, this would be like rho m is equal to rho m0 e to the power minus of, okay, I can just write log of A to the power minus 3, because log of 1 is equal to 0. So I have this one. So now I can say that rho m is equal to rho m0 e to the power log A minus 3 is basically A minus 3. So this is the way to, find out rho m. So now what I can do, I can have this one, this equation, I can use it. So I'm just saying that h square over h0 square is equal to kappa square. I know what is rho m. So I can simply say it is rho kappa square rho m0 over 3h square. And again, we have A to the power minus 3, right? And similarly, I can write, similarly, this equation will also follow this one. And now we have nothing, because P is equal to minus 1, right? So P is equal to minus of rho. This will cancel out. It will become 0. So rho lambda becomes constant. So we have now rho lambda 0. This. So now you may see over here that this is now become your omega m0. A minus 3, A can be also written as 1 over 1 plus Z. So this will become 1 plus Z to the power cube. And I can just write omega lambda 0. And h0 square is over here. So here you can see I have a model of h square, right? So now you can see that we have now found out how to estimate h0 square using our simplified model 1 plus z to the power cube omega lambda 0. Now what is the next step? The next algorithm that our model is done. What we're trying to estimate h0 square. How we can estimate h0 square? We can now vary omega lambda 0, omega m0 and omega lambda 0. Now because it can, now the thing is the energy density cannot be negative. So omega m0 can vary from 0.1 to let us say 0.9 or 1, whatever, because the point is that it has to be 100%, right? Because we have already normalized it. So this is the fraction densities, which can be like 0 to 1. So I am just saying that, okay, 0.1 to 0.9. And similarly, you can say that omega lambda 0 has to be between 0.1 to 0.9. Now you have the redshift. Now let us say that we have calculated, let us say somebody has already calculated, okay, here we have Z. And at some point, some telescope has already calculated that, okay, this is the Z0 from the experiment, correct? So now let us say 0.01, they have calculated, let us say 68.7 and so on. 0.02, it is 70. 1 it is 80, 2 it is considered to be 90, and so on. So they have already calculated these guys, correct? So now for different redshift, they have different H0s, or you can say that whatever the H and so on, correct? So you can say that this is something like H, and they have already estimated it. Now what it says that now we have a model, Z and H is already there. It will try to first, so what is going on that we are using the MCMC sampling, and using this MCMC sampling, what it says that, okay, first of all, I am having H square is equal to H0 square, right? And also it will also say that, okay, H0 can be like 60 to, let us say it has to be 50 to 100 kilometer per megaparsec per second, correct? So consider it will have some, let us say, first of all, 50, and then omega m0 consider to be it is 0.1 and square. And first it will try to calculate Z1, okay, Z2, Z3, and so on. And it will try to estimate that what is 1 plus, let us say, 0.01 cube, and omega lambda 0, it can pick anything, let us say 0.2. There is nothing. So first of all, from here, it will try to calculate what is your H. And let us say it is coming out to be 72. And then it is a theoretical value, right? And from here, it will try to estimate H minus S theoretical, and you will get some value. And there is an error which was already there in the measurement of H. So it will try to use chi-square, which is H minus S theoretical over error. And it will try to reduce this chi-square. Suppose that now it is coming very much, let us say it is 100. Now it will try to pick different of omega 2, omega m0 to be 0.2, now omega lambda to be 0.1, H0 to be 50. So as you can understand that as you're increasing your parameter, there are a lot of combinations is possible. And now your parameter estimation is 50 to 100 kilometers. That is why you have to also you have to say that, okay, what should be the steps that you are saying? So you can say that, okay, my step has to be 10,000, because if you are not using the 10,000 steps, means that it is trying to, pick some 0.01, 0.12, 0.100, and so on. And it is, try to use the various combination. And there is again a n workers. N workers says that, let us say you have the blue ball. These are workers. Okay, they will try to, point out the values at different combinations and try to minimize this chi-square. So when the chi-square is very much minimized using the steps that you have already given that. So if your chi-square is coming out to be, let us say 1, and reduced chi-square is let's say is lesser than 1, then you can say that, then you will the corresponding value of omega m0, obviously you will get some value of omega m0, omega lambda 0, and H0. Then you may say that, okay, this is the value that I am interested, and this is the true value of H0. Correct. So what is the algorithm? Algorithm is that first you have to have the model by solving the equation of motions, and from there you have the different data sets. What I am going to show you, the different data sets and so on. So first of all, very much lecturing, and I'm gonna first show you that how it is happening. So we have here there are different Python libraries, because Python is so much easy and you can do, because all the things have been already doing in Python. So we are using the Python. So first of all, you have to import from Numpy. Numpy is a library. From here we are using square, and also we are whenever we need to use the Numpy, we can again just simply call import Numpy as MP. So you can just say that, okay, numpy.np.py and so on. So these are the things you can take a screenshot from here, right? And now here is the various data sets. First of all, there is an OHD data sets in which you have the one column for the redshift and another column is for the Hubble. So I'm just showing you that what is this OHD data set. So now you can see that this is the OHD data sets from the different supernova. So first column is the redshift, and this redshift have just going from 0.0708 to 2.36. In the second, we have the different H0 values. Okay, it is it has taken from some paper where they have already been it that what should be the Hubble. And now whatever the data they have, there is an error on the estimated data. So these are the 43 data that you have. And now you are trying to make a model and in order to try to minimize it. Okay. So now what happens is that we have the error file. Okay. So here you have the, okay, now we have OSD data and there is an error. Use column is equal to 0. It says that 0 column. Use column is equal to 1 column, and use column is equal to 2. It is the second column. Now, another way is that another data is we have the Pantheon data, because this Pantheon data is from the SUS data, who is, the race. The Rees has been awarded a Nobel Prize in 2011 for the discovery that, okay, we have that he has already made in 1999, that universe is accelerate, the expansion of the universe is accelerating. So he has bigger telescope which actually measuring directly the H0. It is trying to estimate what should be the H0 of the H0 from different sources like supernova, and that is called the direct measurement, the Cepheids and different and other things, right? So in the Pantheon data, let us say I'm going to also show you the Pantheon data set. So here, over here, we have the Pantheon data 0.0. These are the redshift, and from here, these are the luminosity distance. And over here now, there is an error bar, right? Because when you are trying to measure the supernovas or Cepheid variables, you are just measuring the distance modulus. Let us say from the, you have the brightness, and from the brightness, you are trying to measure the distance modulus and so on. So that is the thing we are trying to see. So there is a Z2. Again, we have different data shift. That's why we are labeling as a Z2. Use column 0. Luminosity, that is a luminosity distance, we use column 1, and there is an error of this error from here. Now what we have to define is that the way we have defined is the parameter space. So this is the paramus, which is parameter space. So for an example, we in our model we have H0. So we have said that, okay, this value should be come around 70. It does not. It is not required. It has to come around 70. Minimum it can go 60. Maximum it can go 80. Right. Now, since I have developed this code for the scalar field, that's why I have to choose in such a way that it is the scalar field has to run. Otherwise, it can go to infinity and there is no use. Right. Now from here you can use parameter dot add again omega m0 and omega lambda 0, and similarly h0. We have whatever the parameter that you want to estimate, you want to it will create some kind of an ensemble. Okay, so there is a various points from minimum to maximum, and it will try to randomize it and try to see that, okay, which value is actually closing it. So it is more or less very extensive data analysis part. Now over here we have defined some kind of equation which I'm talking about later on, and then there is an chi2na. Chi2na just say that, okay, we are trying to estimate the chi square, and here goes your model, and then over here I am just calculating over here h, right? So from here, from the scalar field, over here I am calculating the Hubble, okay, using the H0 variation and the parameter that is called delta. Delta is the associated parameter from the potential, and over here I am getting the Hubble value. And once I have getting the Hubble value, I am just saving it as a text file. This Hubble value, as you can see over here, this is the Hubble value that I am getting, which is 77.4. E plus 0.1 means that it is multiplying with 10 to the power 1, which is 77.476. So this is, you see that I am getting from z is equal to 0.01 to z is equal to 0. So over here, what is basically happening is that I am integrating, because I have to integrate it, and I am trying to measure theoretically using VH0 and so on. So this is my theoretical H. I am saving it, and again I am using H in my chi2 square, H minus SD, which is again from the data over error. And then what happens is there is a minimizer. So now in minimizer, it will, this is the main program. So from here, there is your MCMC going. So the MCMC method we have chosen is, the sampling method is EMC. We have seen that, okay, what should be the burn? So burn, as you are increasing the burn, then you have, that okay, you can just relax and you can compute. So do not, mind if anything goes up and down and so on. So there is a NAND policy, omit, and then step size. So we have now, for example, step size, we have uses 2000, and there is an N walkers, means that there are some kind of, something is working inside this sampling. It will just try to pick all these things, and then it tries to minimize it. So the minimizer is taking this function, which is we have already defined as chi2na. Inside the chi2na, there is everything which is chi, because we are returning chi2. It will take this one. It will use the minimizer, because I am using the minor.minimize. We are trying to minimize it using the EMC. So let us say I am showing you that, let us say we have 100 and N walker could be 15, and I'm trying to run this program, and you will see that the magic which you have waited for. So now this is the way it will run, correct? So for the 100 step, it will taking the for one iteration, it will taking 5.18 second and so on. So because this program is, we have made it very simplified and we are using the only one data set. Okay, so because the data set is very small, so I have to make it, let us say 500. So this thing you can always get, because when you have using the lesser data set, you have to, make it again, bigger, that okay, your model is very much simplified, so it cannot, if you do not give the you the proper steps, then it will not return you the result, right? So we have to just give it everything properly. Okay, yeah. The one thing I have to mention, that when you are trying to work with this data, again, working with the data is very hectic. I was working and fixing the error, writing the program. We have written the program that I had modified different ways, and again estimating that, suppose when you're using the fluid model is a kind of a very easy one. If you are using the scalar field model, it is a very hectic process, and in many paper you can see that people are using the fluid model, in which you can you can solve the continuity equation and everything is there. But I'm showing you right now that what will happen if you work with a scalar field. In a scalar field, everything is dynamical, right? We have, let us say, a couple differential equations. So the here the program is trying to, first of all, it will trying to calculate the differential equation, and then from a differential equation you are trying to estimate the h0. Now if you are not given the good initial condition, or your parameter is off the mark, then differential equation won't run. It will give you the infinity value, and then everything is boom. So now you can see that when we have increased the step, there is no any error. And the magic is over here, that, okay, we have used something. There is a tau, there is a correlation function that it says that how the worker is forgetting whatever the previous value usually after the 51 step. So the fitting method is EMC. The function evaluated is 7500. Data points are 43. Variables are 3. Right. So the chi-square is estimated to be around 3000, which is again not good. Reduced chi-square is 69. So we think that if we are increasing the number of steps like 2000, or maybe 10,000, then we can have this one. Now, archaic info criteria, this is also a very good information, right? AIC is called, it should be, like 160 and so on. For Lambda CDM model, it has to be, I don't know, something like. Now the Bayesian info crate. So these are the very important statistical stuff, which is very much important in order to justify the model, in order to justify that your model, whatever you have proposed, is good or bad. Now you have calculated that, okay, from this different data sets, H0 is 79. Okay, obviously, because our step is not too greater, you cannot say that, okay, this is a very good fit, because you have to define that what is your chi-square. So if chi-square would have my 1, then I can say that, okay, it is a very good fit. Like now the lambda value is 0.179 and M is this one. So now I'm showing you the magic, that suppose that, okay, let's say we could have found that amazing, data. Let us say, I am just saying that whatever the data that we have already found from the observation, and let us say that this is the thing we are going. Okay, so my theoretical is now become SD, and try to run this system again, and then you will see the first of all, because it is taking time because of the calculation of the all these things. But the thing is that people, the machine is not knowing that what we are actually doing, right? Yeah, because the thing is that something terribly happened. That's why I'm waiting these messages, but it doesn't matter, because my chi2 is already changed. So what should be the result, right? So we can see that, okay, chi-square has to be 0, right? And reduced chi-square should be 0, because we are actually doing nothing. We are simply giving you SD minus SD, which is the observation minus this one. So each and every point has to be the same point. So we are fitting, not from a theoretical, we are fitting observation with observation, right? So let us wait and see. It is taking a lot of time, because obviously there is something infinity has occurred in the program, estimating the H0. But okay, obviously you should not do it. You should not play with the data, and do not try to, my advice would be that do not try to do something wrong with the data, right? If you're using some data, try to publish it that, okay, I'm using this one. Now over here, you can see that chi-square is 4.3 in 10 to a minus of 249. You can see the chi-square, and reduced chi-square is 0.0. Archaic fitting is minus 2.47. So if you have the AIC is negative, it means that your model is extremely fine. So we are not using any model, you're just using the same thing. Like H0 is coming out to be 68, 10.15% deviation. and then lambda value is 0.38. I don't know why it is calculating the lambda value, but it does not have any meaning, right? So you see that this is what happens. Okay, that if you have a very good model, then this is the value that you should expect to this. Okay, now the second part is that, okay, if we have the scalar field, how we can work with the scalar field, and then I'm going to show you that, okay, what we have done in this code. Okay, so let us jump into the scalar field. Right, so the simplest scalar field is we have quintessence, correct? And for the quintessence, we are going to use potential to be v naught e to the power minus lambda, let us say over here, kappa into phi, because phi is the dimension of mass and kappa has mass inverse. So we already know that exponential has to be a dimensionless argument. So this is the what we have to adjust it, right? Now for the quintessence, if you have already worked it, the field equation that you can already get 3s phi dot plus dv over d phi, right, is equal to 0. And over here we have 3h square is equal to kappa square rho m plus rho phi, and 2s dot plus 3h square is equal to minus kappa square pm plus p phi. Now, if you don't know that how we have got this, I have made a video, and you can already you can see my previous videos that how we have got it. Now the rho phi is coming out to be 1 by 2 phi dot square plus v phi, and simply p phi is equal to half phi dot square minus v phi. Now, if you are using the brute force method, you can say that, okay, I'm just implement everything from in this equation, and as it will run, it will try to give you it will try to estimate phi and phi dot, right, from this differential equation using this equation 3h square. And again, what I can do is that, okay, I can say that h square is equal to h0 square, and over here we have omega m0 and omega right, omega lambda phi 0, correct? And with this some kind of function, it will go and it will try to predict whatever my h0, right? But the problem is that you have the second differential equation, and trying to figure out the phi 0 and phi dot 0 is a very tedious work, right? So the problem is, in order to, when you are working with the differential equation, that is the thing. If your initial condition is not very much aligned, then it's a problem. And again, we are sampling it as 0 and as well as lambda. As I have already shown you that if you let us say predict lambda to be 1 and 2, then it happens that this differential equation won't run, and it will give you something bizarre, and then things can go out of the hand. Sometimes it can happen that, okay, 1 by 2 phi square, it can take a very large value, as v phi can take a very large value, and the estimation would go wrong and your h0 completely different. Or similarly, you can say that this equation take maybe sometimes this can be negative or positive, so anything is possible here, right? So in order to do that, what we can use the dynamical system variables. In the dynamic system variables, we can have x is equal to kappa and then phi dot over root over 6h, y is equal to kappa square root of v root 3h, right? X and y is already done, and omega m can be written as kappa square, which is rho m over 3h square. So omega phi would become kappa square rho phi over 3h square, right? So omega phi can be written over here using that one is x square plus y square, and omega n from there you can have 1 minus, because over here 3h square, right? We have this 3h square is equal to, now in this language, 3h square is equal to kappa square rho m plus rho phi. And now when we are refining it, I'm not using rho m0, rho phi 0. So they are now variable. 1 is equal to omega m plus omega phi, right? So omega m I can write 1 minus omega phi is x square minus y square. And there is a total equation of state. This total equation of state is saying that P total over rho total, and you can say that P total is my x square minus y square. Rho total is basically rho m plus rho phi is rho total, right? And if you just divided kappa square over 3h square, kappa square over 3h square, so you can say that this becomes 1, and P total x square minus y square, because P total is basically Pm plus P phi. Pm is turning out to be 0, P phi is x square minus y square. So what you have got? You have got omega total to be x square minus y square. Now, again, when you are using x is equal to kappa phi dot square over square root of 6, you have to find x dot, and then similarly you have to find y dot. Now you can also see my previous videos where I have already determined the dynamical stability of this particular system. So I'm not writing the equation. I'm just showing you that whenever you are writing this x dot means dx over dt, right? So you will get some function in x and y, and then in additional h over here. So when you are working with additional h, dx over, then you will got over here s dt. But my independent variable is in z. So how we can make it in z, into z? So obviously what we can do is, now s dt. What is s dt? S dt is basically dn, which is basically d of log a. Correct? Why? I can write d h is equal to a and dt, and there is a dt. So dt cancel. So I can write dA over a basically d log a, because d log a is equal to 1 by a and dA, right? Now I already have a is equal to 1 plus z. So consider that log of a is equal to log of 1 plus z with minus sign. So I can just say that d log a is equal to minus 1 by 1 plus z and d of z. Correct. So what I'm saying that this is dx over d log a. And what is this d log a? D log a is equal to what we have got, minus 1 by 1 plus z into dz. So whatever you have already written over here, it's going to just a little bit modify. Dx over dz is equal to minus 1 plus z times this. So this is the same thing will happen. Dy by dz is equal to minus of 1 plus z into this, right? And when you are trying to define x0, your initial condition which has to be in such a way that I'm going to show you that how it has to be, right? So 3h square is already gone. So now we have 1 is equal to omega m0 plus omega, sorry, not omega m plus omega phi, which is x square plus y square. Now I'm trying to understand that what should be the x square plus y square. Now we have the dynamical system. Now since if you know x and y, you can easily estimate what is omega m using this 1 minus x square minus y square. So we have the two differential equations, let us say x prime and z prime. Y prime. If you know what is your x prime and y prime, you can easily estimate what is your omega m0. So what we can do, let us say that you can say that, okay, omega m has to be very correct. So if you are sampling it 0.1 to 0.9, so therefore everything will vary. But the problem over here is that, let us say you try to estimate, because first of all, you have to guess something. If you're guessing x, and then you can estimate from there y. So what I'm doing is that y is equal to omega m0 x square, right? And there is a square. The problem is that consider that omega m0 is turning out to be, let us say 0.1, and you are making x to be, initially your x is 0. Let us say 0.01. So it will very much lesser, and then you have got a good thing, right? So now based on it, your y will simply vary. Now in some cases, what happens is that sometimes any of the function can get bigger, and then you will have the square root problem, and then you have y is equal to some different thing. That is the problem. Now the problem is that one of the problem is that delta. So the lambda is the potential thing. So lambda will also vary, correct? So lambda can also vary. Similarly, when can lambda be vary? The lambda can get from, let us say, minus 2 to 2 or minus 20 to 20. But the problem is that if lambda is equal to 0, then you have the constant potential. And if you have the constant potential, there is no, it will consider to be, lambda CDM model type of thing, because you have again a constant lambda, and we don't want it. So we want to avoid lambda is equal to 0. So we can first say that, okay, lambda, let us say minus 2 to 0.1 minus 0.1, and then you can say that, okay, it is let us say 0.1 to 20, and so on, correct? So this is how we have to estimate. So I am going to vary omega m0, and then we have x0. But the problem, you can ask that, okay, we don't have x1 and y1. So how you can vary it? Okay, we can simplify, because when we are using the initial conditions, we can say that we can simply explicitly write it down that 1 minus, and I'm going to make it in such a way that, okay, this has to vary. So this is some kind of number which nobody knows what is this. I can just vary it, right? It is a number, and then there is a x square. But the problem is that, so this is now varying. And if I am fixing this one, let us say 0.01, I have fixed it, or let us say 0.1. And if I am saying that, okay, this has to vary, consider it is 0.9, then what will happen? 1 minus 0.9 minus, let us say, x square is coming on to be, let us say, 1. Then what will happen? Now 1 minus 1 is 0. So now y is equal to 0. So if y is equal to 0, then there will be some problem with the differential equation. And again, you will returning the value infinity and everything is now boom. So this is what happens when you are trying to, work with the scalar field problem. So you have to estimate your initial condition in such a way that everything has to be relaxed. Lambda has to be fixed in such a way that everything is working. And now you can say that there is one more advantage over here, that H0 can be anything right now, because we are not estimating H0 from here. We are just trying to figure out what is x and y. So the problem is that now you may ask that, okay, how will you then get x and y, because there is no x and y is coming anywhere, because you are using the initial condition from y is equal to square root of 1 minus v omega m, which is you are varying it, minus x square. But where is this H0? We can estimate H0 from here, like 2s dot over 3h square plus 1 is equal to minus kappa square 3h square pm, which is has to be 0, and p of phi, correct? So now 2s dot over 3h square, I can write kappa, it is 0, and p phi is basically minus x square plus y square and minus 1, right? So now you may see that I can write s dot like this, dh over h and h dt, correct, is equal to 3 by 2 minus 1 minus x square plus y square. Now ds dt can become dh over h dn, 3 by 2 and so on. Okay, now d can be written as log of h, and when I'm writing log of h, it is a log, natural log, right? And d of n, what we have determined, d of n, basically d of n is equal to minus 1 plus. So dn would become minus 1 plus z, correct, with dz, minus 1 plus z into 3 by 2 and such. Okay, now we are saying that now we have this guy over here, d log h. I can just integrate this one, and I'm saying that everything over here, because we have already found x, y, and z from the differential equation. And if you are trying to find out what is the x, y, and this one, these are the function of basically z, right? Because when you are trying to estimate dy by dt is equal to, let us say, y. So what you got? You got is equal to y solution e to the power t. So it means that when we are trying to solve this differential equation, this x and y is a function of z, correct? So I can say that, okay, d log h, I can integrate it separately, minus 1 plus h, 3 by 2, whatever it is, dz, I'm going to integrate over here. I'm saying that when z is equal to 0, h0 has d log h. So obviously it is, happening with h. So h0. And when z could be anything, because if it is my whim that what should be the z. And over here, I'm just saying that at any z, h would be h, right? So we have now d of log h. What is this d of log h will give? It can just give you log of h. Log of h over h0 is equal to, I don't know what is the integration of 1 plus z, 0 of z, and all these things over here and dz. So how we can get? So I can write h is equal to, because log will go over here, it will become e to the power 0z minus 1 plus z, 3 by 2 everything dh. You see that now exponential to the power anything cannot be negative. So over here we are getting that h can never be negative, right? H is not, because h is showing you the expansion rate. If your universe is expanding, it is always expanding. So now you got it. Now over here h0. So I am going to vary this h0. I have x and y, which is determined by using the variation of the initial conditions. I have the solution. Now what I can do, I will just invoke those solutions, because x has solution which is, let us say, 0 to 3 and so on. We have some plot over here, basically, which is giving you that what is the value of x at different point, right? Similarly, we have y at z at different point, right? Now I'm going to put these solutions or these points at the same time over here in x and y, and z is already there. Now they have become the function of dz. And what will happen? the integral then try to calculate using those points from, let us say, dz. Consider that your data is starting from 0.013, let us say 0.1, 0.2. So you are trying to go from 0 to that point, 0.13, because that is how you can calculate h, right? With the h0, because we are trying to estimate your h, right? Similarly, for dz, z will become 0.1, maybe 0.2 and 0.3. So it will have the map that I had already shown you, right? I'm also showing you right now. I will also show you explicitly. So that is the algorithm. So I'm going to show you that how I have numerically estimated it. So consider these are my equation of x, equation of y, and now equation of h over here, right? Now the sigma is equal to, sigma is basically omega m square root of 1 minus x square y square, because I have changed the definition over here. No problem. X is my function of time. Time is basically showing you the z factor, right? And you can see now I am running it. Now over here I am just simply showing you that what will happen, because we have to estimate the parameter that where the lambda can run and so on, right? So I have made this t goes to minus log of 1 plus z, which is already required, right? And over here there is no requirement of h0 and so on. But now, because in this differential equation I am also plotting, if I am plotting equation of h, which is basically h, then we are required h0, right? So over here when I'm running it, x prime, y prime, now you may see what I am actually plotting. I am plotting x square minus y square. X square minus y square is basically given the equation of a state. Now you can see it is in blue line. So it is basically going from below minus 6, minus 7, minus 8. It is coming from minus 8. The second term is x square plus y square, which is omega phi. Omega phi is coming from 0.6, 0.7, 0.8. So it is going from that at percent, it is z is equal to 0.8. And what happens is 1 minus x square minus y square. So there is evaluation, because we already know that omega m, because omega m is a function of rho, it will increase with because omega m is equal to omega m0 into 1 plus z to the power cube. So as your z increasing, it will increase. So this is shows that, okay, how if the z is increasing, it will also increase, right? And then you can see that 2 over here you have 0.1, 0.1 and 0.2. So it is now coming. So everything is now fixed, right? Now if I try to plot equation of h, so I'm going to write over eqh, and then you can see that, okay, now what happens is that it is below 200. So it has to be like 178 and so on. So this is the h that is actually going. So from z is equal to 0 to 2, we have everything, right? So this is the way we can estimate. So I have generated the algorithm. The first algorithm is try to solve this differential equation x and y, try to get the solution, and then try to use the solution over here in the exponential factor of the solution, and then dz, and this dz will integrate from 0 to the redshift that you have already in the data, right? So now keep in the mind is that, let us say first the algorithm is solve x prime, y prime. You got the solution x and y in terms of z. Then what will happen? Then you have to estimate h is equal to h in this integral, and in this integral e to the power something, and in this integral you have x and y, and now whatever the result you have to invoke over here as a point, and you will try to estimate it at some point z. So what will happen? It will try to create the h, but the problem is that it has to be binning, like it has to be zi. Suppose z1 is 0.01, so it will have hi. I will go to 1, 2, then again 0 to s2, it will estimate again s2 and so on. So it will now proceed on and on and on, right? This is the result. So what I have done over here, what I have done is, again, this video is very much lengthy. So first of all, I have load my data points, experimental data 1. I have over here parameter, paramus is equal to parameter, and then the parameter that I have the values, paramus dot add. So this is how we are adding it. This is for the luminosity parameter, right? Right now it is not no use. Definition of equations. So in the definition, you have, whenever you have the variables, let us say in my x and y as my variable, x and y is equal to y1. Whenever I want to call this definition equation, then y1 will go, right? Over here, ZT is the redshift, right? It is a time variable. Let us say that Z variable. So Z is over here, and lambda value is the, because this equation will depend on lambda. If you are not provide the lambda, there is no any differential equation. It won't run. We have to work it numerically. Omega phi, I'm defining x square y square, omega m0 1 minus omega phi, equation x, the right hand side over here, equation y. So this has to be written equation x and equation y. So basically what I'm writing is dx over dt is equal to this one. dy over dt is equal to this one. So you cannot say that dx over dt minus something. No, it is like dx over dt is equal to this one. Dy over dt is this one. These are the right hand side. Now I am defining chi to na is again a definition. You can name whatever you can write. Now the parameter space that I have already drawn, this is paramus. I am over here parameterizing. Now chi is, again I am making some kind of a list. Why list? Because it will everything, the value will go at this chi, because chi has to be in listing, because we have all the data sets. So right now we are trying to estimate the chi in such a way, right? Now what will happen? We have now v paramus dot value dot distribution. We have to write it over here. Now init is equal to 0.04 and 0.85, and now we have definition which is dsolve, right? So in this definition of dsolve, you have the differential equation. So how we can do? Let us say we have written try and expect. I will show you in the minute why we have written. So this is the z variable, right? When you try to integrate it, that I have already done it over here, that ND solve, it is taking the dummy variable t is equal to minus 20 to 2 or whatever you can write, it doesn't matter. So it can run anywhere, right? As long as it is consistent, because your z is defined between 0 to let us say 3. So now you are actually trying to solve your x and y in a given range. Let us say I'm trying to solve this not from minus 2 to 20 or something. So over here I am using that, okay, just solve it 0 to 5 in order to have a better consistency, right? Now solution ODE, first argument will be equations, second argument will be initial conditions. So I have defined initial condition in the square bracket. This initial condition says that this is for the first variable, which is x, and this is 0.85 for the second variable. Now why I have estimated 0.04, 0.85? From this ND solve, we found that if I am using 0.01, so let us say I have over here 85, right? So I can explicitly see that how everything is happening, correct? So that is why I am trying to use the initial conditions. So if you vary the initial conditions, let us say you have 985 and then run it, then you can see that these things will go on, right? As we have already seen that this actually x0 and y0 basically give you what? Omega phi 0. In other words, it is giving you that what is the matter density at present today, but it is not for today. It is the constant value that we have already, assuming that what should be it. So in the better case, what happens is that these values has to be vary, correct? Because when it will vary, then again I can say that, okay, omega m0 have the some variation in the list, and from this variation I am just picking that, okay, what should be the best value, which is basically fitting it, right? So it is kind of constant that you are trying to predict that what should be the constant. Y is equal to mx plus c. C is a constant. You're trying to that, okay, where it will cut. So depending on, so now I am not varying, but when I will modify, then I will vary it. The problem is now here that initial condition I have supplied, R is the line space, NP to line space says that, okay, 0 to 5 means 1000 space, means that 0.001, 0.002, 0.003, 0.004, and so on, it will go to 5. So as you are increasing the line space between them, the smooth that function will look like, right? So somebody can say pick the 1000 and 1 lakh, but it doesn't matter, right? Why it does not matter? Because you have to see your data. Your data, for an example, OSD, you have z is equal to 0.708. So the precision is 1, 2, 3, 4, right? So accordingly, you have to make it. Let us say it has the four order of significance. So I have to make it 4 order of significance. How I can make? So 1000 is the 3 order. Let us say I can make 10,000, right? So as you are increasing your precision, the more you will get everything to be correctly done, right? So now I have 10,000. And now over here R, now argument is V lambda. Now V of lambda, what is this V showing? This V of lambda is now variable of lambda. So it is taking the value from this parametric space. Lambda value is equal to 0.4, minimum is 0.01, maximum is 0.9, because if I have tried the 1 and 2, the differential equation was not running. So the minimum is that I have set, right? So v lambda is just like, then you have to just make a comma and then close this bracket. If you are not making the comma, then again it will take again some different values, right? And over here there is a comma, it is not required, you can just skip it. Now I'm trying to insert my x solutions from this solution, because in solution there is x and y. So I'm saying that okay, because it will give you the bunch of solutions, right? For an example here, when you are solving this ND solve, we have one column which is giving me x solution, y column is giving y solution, right? So this says that okay, x is equal to solution in this way. From the 0 column will give you the x result, and the 1th column will give you the y result. So I'm saying that okay, returning my x and y, except exception as e, import traceback. It says that you can if you have any error, then it will just give you that where is the error, where you have to look for, right? Otherwise, if you are not giving it, then it will not say that okay, where is the error is occurring in this all this context, all the differential equations. Now differential equation is closed, but we are still this inside the definition of chi to na, because equation is already done. Equation we don't use. Chi to n is a main equation where everything is going on, where your parameters value distribution is happening. Now again I am using ZT. Mind it, whatever you have used 10,000, so you have to also use over here 10,000, because x and y solution is corresponding to that z, right? So now we are trying to extract x and y solution from this dsolve, because x and y you are returning it, so x and y will go from dsolve to x and y over here. Now again we are defining r is equal to line space, because r is we have defined over here. So when you are outside this dsolve, it will not know that what is your r, so you have to again define it r, but it is not used. You can we can also work with the ZT just said. Now what I'm saying is that I try to x value, because x and y, it is taking the x value as a something like plot and so on, right? So I want to try to interpolate it. Okay, so this is the interpolation of the x value that I am getting from this. I have made the solution and now I'm trying to interpolate it. So I have the column of the x values and column the y values. So from here I am just using that r is the line space 0 to 10,000. I have to also use the 10,000, and then again it will make a list between r and x, and again y value, so it will generate some kind of list, right? Okay, now I have used the ZT desired. Now this ZT desired is the Z1. Z1 is, you can see over here, the list that the Z1 corresponding to S0. Okay, Z1 is corresponding to Z of the OSD data. So over here you have the column, this column is basically showing you the Z0, right? Where is this? Z1. Again, SD is showing you that Hubble value from the, in the second column you have got Hubble value, right? So what I'm going is Z is Z desire. Now this is omega phi is no use. Now I'm saying that, now first of all I need to calculate the integral, and this is the very important point. So I have the list in which there are 43 values of Z, right? So what I'm saying that okay, I need to calculate those H, right? So it means that every time your integral, just like I had told you, that integral this 0 to Zi, and Zi is the points at which it will try to integrate it, correct? So let us say I want the integration from 0 to 0.0708, and it will give you the some kind of H, right? So every time this value will first it will go from 0, then it will take 0.09, then it will take 0.02, and it will give me the H, the corresponding H. So first of all, I am just solving the integral, right? So I am just again saying that okay, this is the R evaluation. R evaluate for, because when we are because we are now numerically integrating. So when we are numerically integrating, let us say x into dx, what I am going to write is that trapped, right? And then there is a function over here. What is the equation over here? And then what you can say that okay, x dx, right? So let us say equation over here, and then I'm going to define it. Okay, x 0, where you want to go? Okay, I am saying that I want to go to a point, let us say 0.01. In how way, how many steps? Let us say 1,000 steps I want to, right? So what is saying the integral result is equal to trapped. This is the function in which I am writing your everything which is after the exponential one. Okay, 1 plus r e value because it's already there inside the exponential one, correct? And then there is a re value. Re value says that okay, you have to go for 0. It will automatically understand that you are what is the the value which is at is basically z, because in numerical it does not care about what is x, y, z. It's just seeing your the value. So what is this x value then? Now this x value it is taking off interpolation of this one. So now you have the bunch of list. So it will try to take all the list over here, right? Because you have the complete solution of x and y. If you do not have the complete solution, then how it will know that okay, which we because you have to understand, right? In order to, let us say that suppose I want to integrate, let us say dx over dt is equal to 2x. So it will give you it will try to tell you that x is equal to, let us say, e to the power something. Now I am going to integrate this one. Let us say y is equal to integrate of x into dt. So I will again, what will take, I will just use this function and then I will integrate it. So that is the result, that we have to understand that what should be the complete value of this one. So I'm just invoking that okay, all the values just come here, right? And then you have to evaluate our evaluation at this point. Now the one thing is important is that first of all, for I in this one, I is the running indices in the length of z1, the range which is length of z1, which is 0 to 43. So the point is over here, point is equal to z1 of I. z1 of I just will list down that okay, for I is equal to 0, z1 of 0, and then this point is over here, right? So where we have evaluated this, okay, so R evaluated 0 to that point go in the 1000 steps so that my error is very less. And then from here, Hubble is equal to V of h0 into np dot exponential of this integral result, right? And then what I'm saying that, okay, Hubble value dot append, because I want to again make a list, because if it is inside a 4, so every time the Hubble will, change its value. And when it will reach to 43, then it will have just only one value. But no, I don't want it. I want the whole complete values. So what I can do is that, okay, first of all, I have defined Hubble value is equal to the square bracket is just representing a list. And then what I am doing is that, okay, Hubble dash value dot append is equal to Hubble. So it will make now create a list. Forget about this one. And now I'm going to save np.test file Hubble slash value dot text, Hubble slash value, because this is the Hubble value which is already trying to, so I am trying to make it into a list. And what is the value? So this is the Hubble value that we are trying to incorporate in this thing. So this is the file name and this is the function name that we are using it, right? So now what I'm going to do is that, okay, now I'm defining another h in which I am again loading this one, np.load file hp value txt use column is equal to 0. And from here, what we are doing is that we are defining chi2 h minus sd, h have list, sd have list, er have list. So now you have chi2 have a list, and I am returning chi2, right? And then over here, minimizer chi2 and this is the function that I am going to parameter space. It will take nan policy omit, step is 500. You have to make it 10,000, better to 50,000. N walkers to be like for 50,000 it has to be like 200 or 300. And then fit logistic minor.minimize emc burn and report fit. Over here, if you want to plot, because there is a corner plots and all these things, then you have to omit this one, this part and this part. I commented out. So it will try to fit the result from the logistic chains, right? Because logistic chains are h0, omega m0 and omega m, whatever the way you have already defined over here, that what serial, let us say h0, lambda value and omega, these are called the chains. So what should be the good value? So there will be a corresponding contour plots. So these are just a customization that of which color you want to use and so on. Now it will just create fg dot figure, the figure, because that is, we are using number of walkers and acceptance of fractions, right? And our program is now done. I hope you like this video. After some time, I am uploading the video. I will try to bring something on the table which is kind of crucial at point of view of researcher, right? So if you're using if you're working with the data cosmology, then you can also to comment on the way, because right now I'm starting to work with data because I'm a more of like a theoretical guy. So let's meet next time and we will discuss so many amazing things. This is the Manado Cap signing out.